Zero-day brief.
Picture this. It's 3 a.m. on a Wednesday.
Right, the absolute worst time for an IT alert to go off.
Oh, exactly. So somewhere in a heavily air-conditioned colocation cage out in Ashburn, Virginia, a trusted enterprise backup agent just wakes up.
It's just doing its nightly routine, right?
Yeah, exactly. It checks the automated schedule, resolves a customer's host name, and opens a TCP socket to port 22 on a remote SFTP endpoint.
Okay.
It sends an SSH banner, the server responds, and the handshake begins. But that handshake never actually finishes.
Because the server on the other end isn't actually playing by the rules of the protocol at all.
Right. Instead of a normal response, the server sends back a packet with a length field set to, well, roughly 4 billion.
4 billion bytes.
Yeah. The backup agent reads that massive number from the network wire, adds a tiny bit of overhead padding to it, and because of this weird quirk in how computers do math.
The 32-bit wrap.
Exactly. That massive number wraps all the way around to just 5. So the agent politely asks the system for 5 bytes of memory.
Which is nothing.
Nothing. And then it just blindly reads the full 4 billion byte payload straight into that tiny 5-byte slot.
Which is, it's a complete unmitigated catastrophe for the system's memory.
Total.
Because that backup agent was just owned. Utterly compromised by the very server it trusted to receive its data.
The server it was literally paid to protect. So, welcome to the deep dive. Our mission today for you listening is to unpack this massive, totally invisible vulnerability hiding in a piece of code that is...
It's likely sitting in almost every network on Earth right now.
It really is. We're looking at a bug designated CVE-2026-55200, and we've got a huge stack of sources we're pulling from today to make sense of this.
Right, we're looking at the vulnerability reports from unchecked, the NVD, and the actual GitHub pull request, which is PR 2052, by the way.
Yep. Plus, we are pulling from recent news coverage in the Hacker News, Cyber News, Cybersecurity News, and a really crucial advisory from NHS England Digital, which is CC 4799.
Yeah, that NHS advisory is going to be super important when we get to the mitigation steps later.
For sure. So this bug is carrying a CVSS score of 9.2.
Wow.
Yeah, and just for context for you, the common vulnerability scoring system tops out at 10.
Right.
So 9.2 isn't just some minor glitch. It's a drop everything and wake up the IT team level emergency.
That is exactly how network defenders are treating it, yeah. Because this is a critical pre-authentication remote code execution vulnerability.
Right.
And it resides in this open source project called libssh2.
And right off the bat, we really need to clarify something that's been causing like a ton of confusion in the news coverage.
Oh, about OpenSSH.
Yes, this is not OpenSSH. If you're on your Mac or Linux terminal and you type SSH to log into a server, you're generally using OpenSSH.
Right, they're totally different beasts.
Completely. libssh2 is a client-side C library. Developers use it when they want to build SSH or SFTP capabilities directly into their own applications.
Right, so they don't have to shell out to a separate, bulky program.
Exactly. So it's distinct, but it is everywhere. But to understand why this bug is causing such a panic, we first need to understand that shocking math error that makes it possible.
Yeah, the math is the craziest part.
Okay, let's unpack this. Explain the mechanics of this bug for us without, getting too bogged down in unreadable code jargon.
Yeah.
How does a packet length trigger a full system compromise?
Sure. So the exact failure happens inside a specific function called libssh2 transport thread,
Okay.
which lives in a core file of the library called transport.c. When an SSH client connects to a server, the server sends an SSH packet.
Makes sense.
And that packet contains a field called packet length, and that literally tells the client how many bytes of data are about to follow.
So it's like saying, here comes a box, and the box is exactly this big.
Precisely. Now, the official SSH protocol specification states that real payload should be capped at around 40,000 bytes.
Okay.
But the wire itself, like the physical network connection, it doesn't magically enforce that rule.
Right. It just delivers whatever the server sends down the pipe.
Exactly. So libssh2 reads this packet length value. It does a quick check to make sure the number isn't 0 or negative, which, makes sense.
Because you can't have a negative box.
Right. Then it adds a few extra bytes to that number to account for packet framing overhead.
So just adding a little bit of padding for the digital envelope, basically, the headers and footers of the packet.
Right. But here is the fatal flaw. That addition happens using 32-bit unsigned arithmetic.
Ah.
And if you're familiar with how 32-bit numbers work in older programming architectures, you know they have a hard physical ceiling in system memory.
Because there's literally only so many ones and zeros you can use.
Exactly. The absolute maximum value you can store in a 32-bit unsigned integer is roughly 4.29 billion.
Okay.
So if you take a number right at that ceiling, say 4 billion, and you add 5 to it in 32-bit math, it doesn't become 4 billion and 5.
It rolls over.
Yes. It works exactly like an old mechanical car odometer that reaches its maximum mileage. It wraps around past 0.
So 4 billion plus 5 just becomes, wow, it just becomes 5.
The arithmetic just completely wraps around. The code takes that resulting number, the number 5, and it uses it to allocate memory.
Oh, no.
Specifically, it allocates a tiny 5-byte buffer on the heap.
And just to pause on that for you listening, system memory is generally split into a few areas, right? But the two main ones are the stack and the heap.
Right.
The stack is very rigid and orderly, mostly for keeping track of where you are in a program.
Yeah.
But the heap is like the dynamic sandbox.
Yeah, it's where things get messy.
It's where a program says, hey, operating system, I don't know how much data I'm getting, but I need some space right now.
Yeah.
So libssh2 asks the heap for 5 bytes of space.
But remember, the payload actually streaming over the network wire is still 4 billion bytes long.
Right. The data is still massive.
So the library code proceeds to read those gigabytes of attacker-controlled data into that tiny 5-byte slot.
Which obviously doesn't fit.
Not at all. It immediately bursts out of that tiny allocated space and violently overwrites everything sitting next to it on the heap. Function pointers, metadata, other application data, it just paves right over it.
It's a classic out of bounds, right?
Yeah.
I mean, imagine you walk into a restaurant you've been to 100 times.
Okay.
The host greets you, asks how many in your party, and instead of saying 2, you hand the host a napkin that just says 4 billion.
Right.
The host glances at it, their brain does some bad 32-bit math, and the number wraps around. They say, a party of 5.
Perfect analogy.
They clear a small table, push some chairs together, set out 5 silverware roll-ups, and then open the back door. And 4 billion people suddenly fled into the restaurant.
And they don't just flood into the dining room, they flood into the kitchen, the manager's office, the safe.
Yeah.
Every corner of the building is suddenly full of people you never invited, touching things they definitely shouldn't touch.
But, okay, memory corruption is one thing, right? Remote code execution is another. So they flood the kitchen and the manager's office. How does that actually let the attacker take over the server?
Well, what's fascinating here is that the people flooding the restaurant don't just stand there. In system memory, the data your program is processing and the instructions your program relies on to function, they live right next to each other.
Oh, I see.
So the overflowing crowd pushes the restaurant's actual manager out of the way, picks up the manager's clipboard, and starts giving their own orders to the staff.
Wow.
In computer terms, they overwrite what are called function pointers. When the program finishes its current task and looks at that pointer to ask, what instruction do I execute next? It reads the malicious instructions that the attacker just wrote into memory.
The attacker literally rewrites the script the program is following.
Exactly.
But hold on. The S in SSH stands for secure. We're talking about a protocol famous for host key verification, encryption, cryptographic integrity. How is a server owning a client before a login even happens? The vulnerability reports explicitly say this is pre-authentication.
This is an incredibly common misconception about SSH, and it introduces this concept known as trust inversion.
Trust inversion.
Yeah, so SSH is absolutely brilliant at protecting a connection from eavesdroppers. It keeps third parties out.
Right.
But the client inherently blindly trusts the server it is choosing to connect to. The trust model flows entirely in one direction.
So the encryption is protecting me from a man in the middle listening in, but it's not protecting me from the person I am actively talking to.
Exactly. You verify the server's identity, you establish an encrypted channel, and then the client just becomes subservient to that channel.
It just does what it's told.
The server generates the packets, and the client dutifully consumes them. libssh2 was designed to connect to servers on behalf of an application. It was never architected with the paranoid assumption that it had to defend itself against a malicious or compromised server. One that's sending poisoned, oversized packets on the wire. There is simply no structural defense for it.
That is terrifying.
Yeah.
Just a simple 32-bit math error causing total system compromise. But as I was digging through the National Vulnerability Database archives for this deep dive,
Oh, you found the 2019 bug?
yes, finding out it's a simple math error is bad enough, but finding out it's a repeat offense is so much worse.
And this is where the history of this code base becomes highly relevant and honestly a bit frustrating for security researchers.
Totally. So Tristan Madani found this bug in June of 2026.
Right. He found it, filed the pull request on GitHub again, PR number 2052, and sounded the alarm. But this exact function, SFTP transport,
Exact same one.
and this exact unchecked packet length variable, it was successfully exploited 7 years ago.
7 years? I mean, that's a lifetime in tech.
It is. In March 2019, a researcher at Canonical named Chris Colson found a massive batch of 9 vulnerabilities in libssh2, and the headline bug of that entire batch was CVE-2026-55200. It was an integer overflow in the transport read function that led to an out-of-bounds write.
That is literally the exact same description as the bug we were talking about today.
Yeah.
Down to the function name.
Because it is the exact same attack vector. A malicious server sending a crafted SSH packet with a massive packet length value to trigger an integer overflow.
So what did they actually fix back in 2019?
Well, the fix they applied back then was highly specific. They patched the one arithmetic path that caused the specific overflow Colson demonstrated.
Oh, no.
But they completely failed to add a ceiling limit to the packet length variable itself.
It's like a house with a row of identical doors. Someone kicks in the third door, so the homeowner puts a heavy-duty deadbolt on just that third door.
Right.
They dust off their hands and walk away. 7 years later, an attacker walks up and kicks in the fifth door. Why didn't anyone just reinforce the whole frame?
Yeah.
Why didn't they put a bouncer at the front door to check everyone's ID before they even got into the hallway?
That's exactly the blind spot of the libssh2 architecture at the time, and it highlights a much broader problem in open source maintenance.
Which is?
Maintainers are often overworked volunteers. They play whack-a-mole with the exact bug reported to them rather than refactoring the underlying architecture.
Because they just don't have the time.
Exactly. They assumed the SSH protocol specification, which, remember, says packets shouldn't be bigger than 40,000 bytes. They assumed that would act as a natural deterrent.
But the wire doesn't enforce that.
Right. They failed to put a validation gate, your bouncer, at the parser boundary to actually enforce that 40,000 byte limit in the code itself.
So they trusted data coming from the outside world without sanitizing or verifying it first. I mean, that's the cardinal sin of programming.
It really is. And that specific lack of boundary validation didn't just cause this one remote code execution bug. According to the Vulncheck reports, it caused 2 companion bugs in this exact same 2026 batch.
Well, there are more.
Oh, yeah. There is CVE-2026-55100, which is a severe denial of service loop.
Okay, how does that one work?
A malicious server can send a malformed value during the cryptographic key exchange phase. Because the client doesn't validate the boundaries of that value, it enters a while loop that it can never resolve.
So the client's just desperately trying to parse data that makes no mathematical sense, and it just gets stuck.
Stuck completely. It spins a CPU core at 100% capacity for over 60 seconds per connection attempt, completely freezing up the application.
Wow.
If an attacker spams that connection, they can permanently lock up the server hosting the backup agent or the app.
That's brutal.
And then there's CVE-2025-15661, which is a heap overread in the SFTP layer.
An overread. So instead of writing too much data into memory, it's reading too much out.
Yes. The server tricks the client into reading past the end of the data buffer it was supposed to read.
Give me an example of what that looks like.
Imagine asking a program to read a 10-word sentence, but it doesn't know where to stop, so it just keeps reading the invisible ink on the back of the page, the next page, and the page after that.
Just vacuuming up whatever's nearby.
Exactly. It ends up pulling adjacent data from system memory, which could include encryption keys, passwords, or session tokens, and leaking it. All of this happens because the client unconditionally trusts what the server tells it to do.
Okay, but here's where it gets really interesting, and honestly, where it usually confuses people outside of IT.
Okay.
If the fix for this commit, 97apps3d, was submitted to the GitHub repository, why is everyone panicking? Like, if my Linux server is up to date, aren't I safe? I just run my package manager, do an apt-get update, reboot the machine, and go to sleep, right?
I really wish I could tell you yes. But this is where network defenders run into the nightmare of the static linking shadow.
The static linking shadow. That sounds ominous.
It is. Remember how we established earlier that libssh2 is a C library?
Yeah.
It's not a standalone application with a nice, neat icon on your desktop. It is a building block. It powers common tools you use every day, like curl, git, and PHP. Now, sometimes a library is dynamically linked. That means your operating system keeps one single updated copy of the library in a shared folder, and all those applications just reference it.
Okay, so if you update the operating system, you fix the library for every app on the machine. That's the ideal scenario.
That is the ideal. The package manager sees it, updates it, and you're secure. But in the enterprise and embedded world, vendors very frequently statically link libssh2.
Uh-oh.
That means when they compile their software, they take the library's raw code and they bake it directly into their proprietary binary executables. It becomes permanently glued inside a single massive file.
Oh, wow. So it loses its identity entirely. It's just generic code hidden inside the app.
Think about the blast radius here. We are talking about enterprise backup agents like the one from our Ashburn scenario that reach out via SFTP every single night to push data. We are talking about network switches with SSH-based management interfaces, Internet of Things security cameras, CI/CD pipeline runners that developers use to deploy code to the cloud. We're talking about abandoned firmware on medical imaging devices running deep inside hospital networks.
Which means my standard package manager, my automated updater, it can't see this code at all.
It is entirely invisible to your operating system's package manager. In fact, even your expensive enterprise vulnerability scanner might completely miss it.
Right, brilliant.
Yeah, the scanner scans the network, looks at a server, sees a proprietary executable file called backup-agent.exe, and moves on. It doesn't know what ingredients were baked into that cake 3 years ago by the vendor.
So it's just a black box.
This is a massive builder's blind spot. In recent years, the industry has pushed for SBUMP software bills of materials, like an ingredients list for software, but for legacy and proprietary systems, those just don't exist. You have highly vulnerable code sitting on a critical server, and nobody in your IT department even remembers installing it.
And to make the stakes crystal clear for you listening right now, the attackers aren't waiting around for vendors to issue patches. According to the security advisories we reviewed, a public proof of concept, a POSI scaffold, is already live.
Yeah, that happened fast.
It was published on GitHub in a repository literally called Exploitarium. It provides the exact packet structure needed to trigger the 32-bit wrap. The clock is ticking, and threat actors are actively scanning networks, hunting for these invisible outbound connections.
They know perfectly well that finding statically linked libraries is a nightmare for defenders, which means those vulnerable devices will likely remain unpatched for months, if not years. It is an incredibly lucrative attack surface.
So what does this all mean for you? If you are the listener who has to walk into work today and defend a network, what is the actual move?
Synthesizing the guidance from the advisories, especially the stringent protocols released by NHS England Digital, who are dealing with a lot of vulnerable healthcare devices, there is a 4-step playbook you need to execute.
Okay.
And step 1 is the absolute hardest: inventory.
And let's be real. For you listening right now, step 1 is going to be a massive headache. You can't just run an automated network scan and call it a day because of that static linky shadow we just talked about.
Right.
You're going to have to get on the phone.
You absolutely have to interrogate your vendors. You must manually audit every application on your network that makes outbound SSH or SFTP connections. You have to open support tickets and ask vendors explicitly what specific version of libssh2 is compiled into your firmware, what version is baked into your database replication tool. You have to force them to check their own build pipelines.
Step 2 has to be patching. But I'm guessing based on that GitHub PR, it's not a smooth process yet.
It is currently quite chaotic, honestly. As of this briefing, there is no official finalized tagged release of libssh2 that contains the fix.
So there's no version 1.1.1.1.2 you can just click and install?
Nope. IT teams must rely on vendor backports. You need to keep a close eye on testing branches like Debian's testing repository, which has already pushed repaired builds.
What about the NHS guidelines?
If you are in healthcare or critical infrastructure, apply the specific mitigation guidelines from the NHS England Digital CC 4799 advisory immediately. And if your team builds your own containers or compiles your own software, you need to pull commit 97 ACF3D from GitHub and manually apply that patch to your own build pipelines today.
Okay, so inventory patch. What's step 3?
Restrict. This is network-level triage to stop the bleeding while you figure out your inventory. You need to lock down outbound port 22 and port 2222.
Okay.
If your backup agent only legitimately needs to talk to 10 known customer IP addresses to do its job, you configure your firewall to block it from talking to absolutely anything else.
Egress filtering. Pin the host names. Pin the host keys. Just shrink that attack surface down to a microscopic point.
Right. Now, it won't save you if one of those 10 trusted destination servers gets compromised by an attacker, but it absolutely stops the device from reaching out to a random attacker-controlled server on the public internet.
Which is huge.
And step 4, monitor. You have to look for the anomalies on the wire. Configure your intrusion detection systems to catch oversized SSH packets.
The 40,000 byte limit.
Exactly. The protocol maximum is 40,000 bytes. If you see a packet coming back to your client that is larger than that during a handshake, it is either a profound software bug or it is an active exploit attempt.
Are there any specific red flags on the client machines themselves that defenders should look out for?
Yes, client crashes are an incredibly high signal indicator right now. Specifically, look in your system logs for seg faults.
And a segmentation fault is basically the operating system throwing a red card. The OS says, hey, this program just tried to touch a piece of memory it's not allowed to access, and it kills the program to protect the system.
Exactly. If you have an outbound SSH client, say, a script that is run perfectly every night for 2 years, and it suddenly starts throwing seg faults and crashing during the initial connection handshake, do not assume it's just a random glitch or a bad network drop. It is highly likely an attacker is actively testing an exploit payload against that machine, trying to get the memory offsets just right to achieve remote code execution.
Wow. Okay, to quickly recap the sheer scale of the journey we just went on, a tiny 32-bit math rapid odometer rolling over unravels 7 years of assumed security.
Yeah, it's wild.
It's a bug that was supposedly fixed in 2019, but because the maintainers only patched the immediate symptom and not the structural flaw of missing boundary validation, it has completely come back from the dead. And now, it is hiding inside statically linked proprietary binaries that our standard security tools are completely blind to.
If we connect this to the bigger picture, we spend millions of dollars and countless engineering hours building impenetrable firewalls. We configure complex rules to stop untrusted actors from connecting into our networks.
Right.
But CVE 2026-55200 proves that in an era of incredibly complex, opaque software supply chains, the most dangerous Trojan horse might just be the trusted, voluntary outbound connections our own machines make every single night.
Which leaves you with one vital question to answer today. What exactly on your network is reaching out over SSH right now? And are you absolutely sure you know what code is powering that handshake?
Thank you for listening to Zero Day Brief.